Can you make a material darker just by changing the structure of its surface? You may have seen blackest black materials like Vantablack, or the more recent black created by MIT. These very dark materials get their light-absorbing properties from their microscopic structure. They're made of an array of vertically aligned carbon nanotubes that absorb up to 99.995% of incoming light and convert it into heat. This isn't actually Vantablack, but it's the next best thing. I'll tell you more about it later in the video. Nanotube arrays are fragile, expensive, difficult to work with, carcinogenic, and have poor abrasion resistance, limiting their applications. They are also unavailable to the average consumer. If there were a way to get similar light-absorbing results on a macro scale, it might solve some of these problems. I've 3D modeled and printed a number of macro-scale surface structures inspired by science and nature that I think have a decent chance of absorbing more light than the material they're composed of. Some of them are designed to work with a glossy coating, and others might perform better with a matte one. A glossy surface introduces specularity that might be useful for reflecting the light in specific directions. The surface can function as a dark mirror, reflecting light strategically and absorbing some light on each reflection. On the downside, it introduces glints of light from certain angles that will hurt the material's overall performance. A highly matte surface does an excellent job of scattering light, which eliminates specular reflections and helps conceal the shape of an object. The downside is that the light can't be intentionally channeled or directed by the contours of the surface. It's scattered in all directions, guaranteeing that a certain percentage of whatever isn't absorbed on the first bounce will be reflected back to the observer. The only way a matte surface can be effective as a very dark material is if it absorbs as much light as possible on the first reflection. To give the matte designs the best performance possible, I'll use Musou Black paint for the coating. It's the darkest commercially available matte paint, absorbing 99.4% of the light that hits it. There doesn't seem to be a market for the blackest gloss paint, so I chose a Tamiya spray lacquer. Let's take a look at the designs and discuss why they might work. Some species of butterfly have inky black wings, and scientists have been trying to figure out how they work. That's why we have these incredible photos taken with an electron microscope. The parallel ridges offer shade from many angles, and the webbing between them allows light to enter a shady cavity with a velvet-like surface where it has more chances to be absorbed. This design isn't a perfect replica, but it should hopefully have the same light-absorbing effect. Anechoic chambers are designed to absorb sound waves using sharp wedges made of foam that absorb sound each time it reflects between their surfaces. The wedges virtually eliminate echoes, which are just sound waves reflecting off of a surface. Since light also travels in waves and reflects, maybe sharp wedges can eliminate light reflections in the same way. Laser beam dumps use cones to redirect the laser light towards an absorbent wall, reducing reflections. Maybe a forest of cones with steep angles and spiky surfaces can direct incoming light further inward between the spikes a few times and absorb it before it finds its way back out. Deep holes are dark, but what shape should the hole be? Triangles don't have parallel surfaces to bounce off of, and they can be tessellated. A bunch of triangle-shaped pits might reflect light downward, and between the non-parallel walls enough times to absorb it before it can bounce back out. Turing patterns are named after the same Alan Turing who revolutionized computer science and came up with the Turing test. These patterns that he studied are found all over nature, including the microscopic structures of black snake scales. They are also found in the wrinkles of your brain where they serve to increase surface area. The added surface area should promote absorption, and the steep walls will shade the floor of the design from most angles of incoming light. Nanotubes work well on a microscopic scale. Maybe there's something about their structure that will work on a macroscopic scale. I have no idea how close my model comes to the actual structure of a nanotube forest, but they are multi-walled, vertically aligned, and have a mix of chiral and armchair structures which should be similar to Vantablack. Parabolic reflectors are excellent at focusing a light source into a narrow beam, or for focusing incoming light to a single focal point. Instead of directing the light to a focal point, I cut the bottom of the parabola off to send all incoming light down through the resulting hole. To contain and absorb the light on the other side, I added a mirrored parabola to direct the light straight down and a cone to reflect light towards the walls. I picked an angle for the cone that maximized the number of reflections before the light could escape from the pit. Between sending the light to a reflection chamber and the self-shading effect of the steep walls of each reflector, I think this design stands a pretty good chance. I'll need a very dark material with a known reflectance to compare my designs against. For this test, I'm using Musou Kiwami fabric. It uses glossy black rayon fibers bundled into 2mm tall microbrushes that only reflect light at the fiber tips. Because the tips are spread out and all of the space between them is jet black, the overall reflectance is only 0.1%. This will be an ideal standard to measure against and hopefully try to beat. I'll place all of my designs in a testing rig. There's no reason it had to look this fancy, I just got carried away in the design process. This is a 3D printed integrating sphere with a ring of LED tape running along the seam. It provides consistent and highly diffuse lighting, ensuring that light hits each design from all angles. This is what it looks like from the perspective of the sample. The hole on the other side will allow a camera to photograph each design under identical lighting. I'll take a raw photo of each design and process the files with a linear gamma curve, so every pixel accurately represents the amount of light reflected. Finally, I'll select the area of each design and apply an average blur to get the average luminance value and plot the results. I'll repeat the measurement process a few times with different camera exposure settings to try and get a more accurate average value. The winner will be whichever surface shape and coating combination manages to get the lowest average luminance value. If any of these designs dramatically improve on the absorption of their control sample, then it's worth testing out further designs. If there's little improvement, then this has all been a very interesting waste of time. Before I reveal the results, this is your chance to make a couple of predictions. Number 1, will changes in surface morphology produce a significantly darker, more absorbent surface? Number 2, which design do you think will result in the largest reduction in reflected light compared to a control surface with the same coating? Number 3, between an extremely absorbent matte black paint and a standard glossy black paint, which do you think will produce the darkest result overall? Pause the video now if you want some time to think it over. Okay, it's time to see if any of this has paid off. Here are the results. First of all, every design was successful in significantly increasing light absorption, so that answers the first question. It is possible to make a surface darker on a macro scale by changing its structure. The best result for a matte coating was the spiky cone design with a 45% reduction in reflected light over the control, followed closely by the triangular pit design. The worst matte performer was the parabola design with only a 30% reduction. Now for the glossy designs. The glossy control had terrible absorption due to its specular surface, so there was a lot of room for improvement. The parabola design that came in last in the matte category is now the first in the glossy category with an 80% reduction in reflected light over the control glossy sample, and a 67% reduction over the Musou paint. The anechoic wedge design came in second at a 72% reduction. The cone design that worked best in the matte category performed worst in the glossy category, with only a 54% reduction. I never expected such dramatic results, and thought that I'd be lucky to hit 50%. For these designs at least, it seems to be more effective to redirect light through strategic specular reflection than to absorb and scatter it on first contact. Using a standard glossy black paint and a design that sends most of its reflections into a trap, I achieved a reflectance that is almost as good as Musou Kiwami fabric. I don't have the equipment to verify this conclusively, but assuming Musou's numbers are correct, then my design reflects around 0.13% of visible light. Not bad for a first attempt. It's the design I spent the most time thinking about, and I'm thrilled that the results aligned with my informed intuition. Did I improve on the cost of commercially available very dark materials? Not really. It costs 18 cents per square inch to print my parabolic design in UV resin, plus the paint. The Musou Kiwami fabric I was comparing against is only 7 cents per square inch and is still the most affordable and darkest option on the market. That could change though. I hope to refine my design and find ways to improve the print quality and paint application to get better results. If I somehow manage to outperform Musou fabric, then I'll enter a domain of materials with astronomically higher costs that the average person can't access. At that point, my design will be the most affordable and accessible option for its reflectance value and the blackest black that the average consumer can get. I'll let you know if I ever achieve that breakthrough. If you see value in this type of experimentation and want to see where it can lead, please like and subscribe. I also have plans to make a super reflective white paint that will hopefully outperform what is commercially available. If you have any ideas for future videos, please leave a comment. I'm always looking for the next idea to do a deep dive on. Thank you for watching.